So, in fact, I would like to take about 10 minutes to tell you about a nice experiment we did with a couple of people. The most important two guys I want to acknowledge here are David Krajinovic, who did quite a lot in terms of strategy and data reduction, and Adrien, who did most of the analysis. And by the way, Adrien is a PhD student and ending his PhD at the end of the year. We're looking for a postdoc. He's a brilliant guy, and you should hire him. So the experiment we made is basically looking at the very high mass ends of the early type galaxies, and Thorsten already introduced the subject, so I guess it will be very easy for me to go through the first few slides where we have, where we have basically in situ versus ex situ star formation, assembly, and basically we have from very low mass galaxy to high mass galaxies a dramatic change in terms of the fraction of stars which come from these two things. So basically, if you want to grow at lower mass, you grow by just forming stars in this component. When you go to higher mass, you have to start merging. Merging becomes important in minor mergers, but also major mergers. So that plot showing you the in situ fraction really drops dramatically, let's say beyond 10 to the 11 or so. And in the same way, the angular momentum, the upper end angular momentum from the stars, the stellar component, is also dropping, statistically speaking. So there's a change of regime where above 11.5 or so, you only find slow rotators. But this is where, these are simulations from Thorsten, but this is also where Atlas really stopped. We stopped around that mass, something like a couple of times the mass of M87. And I was always wondering, what's happening beyond this. So the one thing I want to emphasize is something that Thorsten already said. There is not just a single class towards the formation of early type galaxies in general, but at the high mass end, it's even more complex. It's not because you have a major merger early or late or whatever that you can predict what the angular momentum will be. You really need to know the details. So the one thing at high mass end is that we know from, let's say, z equal 2 to 1.5, the mass is growing by assembling several pieces together by a factor between, let's say, 2, 4, maybe sometimes 10. And that growth is mostly mergers. It's not in situ assembly. So the question I want to ask now is at this high mass end, what is the structure of this galaxy? And also how I can link this structure with the stellar population, the metallicity, and all the nice things we know about galaxies. So one question we can ask, a very simple question is, if we take a giant elliptical, is this standard like oblate galaxies like the fast rotators we see at lower mass? Are these mighty triaxial galaxies, or maybe roughly shaped rollate galaxies? The question, of course, you should ask now is, why should we care about this? In fact, if we know the structure, as emphasized by Thorsten, and we know the orbital structure, we can tell really about the dynamics of mass, but also the assembly. And this is very important. The way galaxies assemble at very high mass will change. The way that they assemble will make this kind of morphology, the orbital structure, different depending on the process that you use. So the change we see is under our epsilon diagram, where the size of the dot shows you the mass. You can see a dramatic change where here you have a mix-up of all masses, and the slow rotators here are high mass. So we should ask ourselves, are these galaxies special in terms of morphology and in terms of assembly? So what's happening there? Well, there have been already surveys, observational surveys, trying to tackle this, and looking at the brightest cluster members, the galaxies in the center of clusters. There are a few data from Sarah Bro, Jimmy, and so on, the Australian team, but these are only a few objects, and the data is what it is with VMOS, unfortunately. There's a very, very nice set of papers, already 5 papers out from the massive survey from Jean-Luc Now, with lots of data on BCGs and massive galaxies. Now, they are basically going between the M87, the massive M87, and a bit beyond. But in terms of really going to the extreme, we thought we should do something with Muse. And that's the M3G project, the most massive galaxy with Muse. So so that I'm leading with Deborah, trying to basically address the dynamical state, the dynamic content, the star formation history, the assembly process of galaxies really where we don't have any clue what happens in this kind of size, mass diagram. So what we do is we start with Atlas 3D. Here are some spirals in the size mass plane, and we go just beyond by taking about 30 galaxies beyond the mass of M7. So it goes up to the 10 to the 12 solar masses and beyond. And to do this, we need to go to very rich clusters, as you can imagine. So here is the richness of Virgo, and what we do is we go beyond minus 25.7 in K, and going even up to a richness of more than 200 in the richest cluster that we know in the nearby universe, which goes up to minus 27 in K. So looking at the massive survey, they have about 100 galaxies, we have about 30 as a target. But in fact, we have more galaxies in the very high mass range than the massive survey in that sense, because of our magnitude cut. So just to show you where the most massive galaxies in the nearby universe are, they are in the shapeless supercluster. This is a huge, amazing structure made of clusters. And at the center of the central one, which of course obviously is not a relaxed structure, they are the most massive galaxy you can find. And the wonderful thing is that they are only 200 megaparsec away. So it looks like a bit further. It's a factor of 10, a bit more than a factor of 10 further away than Virgo, but it's still feasible with an instrument which is called MUSE, because MUSE is so efficient that you can basically tackle these galaxies with the same exposure time that you do with Virgo with other instruments on smaller telescope. The other thing is about MUSE is that the systematics are so small for this instrument. Showing here an example of the M87 velocity field we found, we got from MUSE, where we discovered the presence of a KDC, a climatically decoupled component, with an amplitude of less than 5 kilometers per second, meaning the systematics is about 1 kilometer per second. And that's why we are interested by using MUSE, because of its efficiency, but also because of the systematics. So what does it look like, our targets? Well, they are boring. They are dead, they are big, they are red. And these are color image, reconstructed image from the MUSE directives. Boring. But they are not that boring. In fact, we see the same structure as we see in the lower mass. In here, for example, are some velocity fields, sigma H4. This one is a standard fast rotator. This one is a decoupled core. We have stars going around the long axis with KDCs, kinematically decoupled core. We also have lots of this rotation along the long axis. You see that the rotation is not along around the photometric Mayan axis. So it looks a bit weird. We also have the most massive galaxies I know of, which is the central galaxy in the Shapley supercluster, which is about 100 exposures, something like 300,000 spectra, where the structures are quite amazing. The sigma goes up because you start reaching the dark matter influence within the cluster. And we even have a double KDC, something that turns twice its sign. So what do we do with this? Well, we look at the first result. One of the things is that more than half of these galaxies are protoid-like rotation. So it looks like something is happening at a very high mass. So is this a transition, a second transition? Well, it may be, because in fact, in order to grow further than this limit here, you have to take one of these big giants and merge them together. And maybe this is why we have such strange morphologies. Now, just to be a bit provocative at the end of my talk, we're doing the classical things. We're deriving age and metallicities for these galaxies. We even derive star formation histories. This is an example on a different galaxy by Adrien Guerrou, the guy who needs a job. On this, I think the most beautiful velocity field you ever saw, and probably the most beautiful H3 map of a galaxy ever. This is a bar galaxy, by the way, if you're wondering. And what he did is that with the star formation history, he showed, he reconstructed the maps of the stars of different ages, showing how the galaxy assembled, basically by a merger at high redshift, then developing a bar, and then having secular passive evolution for the next 10 years. So this kind of analysis now is feasible with Muse because of the large wavelength range, and you can really look at the star formation history in detail in 2D. But the provocation I want to make before ending my talk is, I have the impression that we're using the same thing since about 1990. We're driving velocities, dispersion, H3, H4, intensity, age. I think we should move our bets here. We should think differently. I think there's something wrong just doing every galaxy with the same. I mean, the tools are better, the software are better, the algorithms are better, our computers are better. We have more spectra, but we're still thinking with the same minds, and I think that there's some problem there. And I would claim that we need some take-it-or-weighted ideas to promote a different way of looking at how to basically couple directly dynamic, stellar population, angular momentum, all these things together. And there are ways to do this. I can show you some examples after the session, how to do this with the data we have on intuition. So that's it. Thanks a lot.
It's very interesting, the new high mass results. So I was wondering, is your several KDC embedded is due to the fact that your massive galaxy is at the center, the CD galaxy, or is it true for all massive galaxies?
I'm not sure I understood the question, but for that galaxy is very specific. I mean, it's kind of an exotic member of the group. I think it only shows you that statistically you have a chance to get this kind of structure when you start merging big guys together at low redshift. I mean, below is equal to, let's say. But there's, I haven't got time to really look at this double KDC. This was basically extracted last Friday. So I can tell you more a bit later when we have looked at it today.
Glenn?
So one question. Correlateness, I mean, you really think that they are correlated in shape?
So this is a discussion I had with Klaus Lovak because now of course I want to see what the simulations are doing, the lambda CDM and so on. The thing is, you have to wrap the stars around the long axis. You need long axis tubes.
Yes.
And that we see very naturally in mergers, even gas-rich mergers. For example, the paper by Bourneau in 2008, where he formed globular clusters around gas-rich merger, is exactly looking like this. And just to remind you, NH7 is prolate-like. There's a KDC in the center, but if you look at the outer part, it's prolate-like rotation.
Yeah, but
whether or not this means that it looks like a rugby ball and then these galaxies play rugby, I think we need to work on the model.
yeah, but I mean, just to make clear, I mean, you can get easily prolate rotation in an oblate or slightly triaxial oblate system.
Yeah, so what we need to address here is the orbital structure now. I want to know the fraction of orbits, of which kind of orbits do we have at different radii. For that, we need modeling. But I think the challenge is to also link this to stellar population.
Okay, one last question while Glenn sets up his computer. Martin.
So to study also last point, coupling the dynamic of the stellar populations, I mean, it's been 10-15 years at least, people who Schwarzschild model, so we can extend those and attach, to each orbit, a range of stellar properties, and just essentially get exactly what you want out of the modeling, attach essentially a spectral type or a range of spectral type to each orbit. And so the question to model is, why aren't you doing it? When are we going to see those?
So I know part of the answer. It's not easy to do Schwarzschild modeling, and on top, if you add this component, you will add a lot of complexity and degeneracy in the modeling. So there are ways to do this, but it's difficult, and not everybody can just run Schwarzschild models because you need to understand them, otherwise you can just go crazy. What I'm advocating for here is a much simpler view. There are ways to combine the data we have. We have LOSVDs, so it means we have mass of stars per velocity beam projected on the sky, per age, per metallicity. And we can combine this into a robust measurement that we can directly compare with simulations without doing Schwarzschild modeling to address the assembly of galaxies. I'm pretty convinced that this is not very difficult. Instead of relying on structured models which are hard to do on, let's say, thousands of galaxies like for MANGA 7.
Let's thank Eric again. We now have Glenn Sullivan telling us about dynamical decomposition of galaxies across the galaxy.
So thanks, Eric, for the last sentence, because actually I want to make a statement that it's not difficult to do swatching models for hundreds of galaxies, because we are doing it. And to come back to Martin, indeed, there's a long time we already wanted to combine swatching type modeling with stellar populations, and I also think we know how to do it. Yes, it's just a matter of finding the person power and because it's required a lot of testing to make sure that you're doing it right. Okay, so a lot of introduction has already been done on why we want to learn something about orbit structure. So let me take a slightly different perspective, and that's actually to go to the beginning of the meeting where we were talking about all these different mechanisms, and we're called quenching mechanisms. I don't like to quenching because it's one particular site to me. I would call galaxy transformation mechanisms, because we all are familiar with morphology density relation, and it tells us at least that at some point we have to turn blue disks into red spheroids. Yes, and this will be environment dependent, but of course there are many different ways of doing it. There are just a few listed there. It can be internal, could be fading, feedback, stellar, or AGN. It can be directly an environment effect from land pressure slipping to tidal interaction, but it can also be more strong tidal interaction, I would say mergers, and merge of course with major minor, etc. So these are all possibilities. And of course the question is, can we disentangle them? Because it's unlikely that only one will operate. So what we want to know, can we disentangle them, can we see the different way? And so these mechanisms have different effects on galaxies, and we know this already from photometry, obviously, but my point is we want to go beyond photometry, and of course we have to do it the first time, but also I would say these have different effects on different components within a galaxy. And so for that we need a robust decomposition. So what I'm going to talk about is trying to do this dynamically. And what we have been applying this to is the Khalifa survey. Ria showed the similar plot as an example of the kind of kinematics, stellar kinematics we have within Khalifa. And I draw here an arrow on it, and at a certain point we want to know if these spiral galaxies, blue disk, turn into the red or spheroids. So with these kinematics, you can make dynamical models. And here's a movie made by Remco. So there are here 3 points to make on the graph. So if you first focus on the movie, because it's an image, what is shown here is an orbit-based dynamical model of this galaxy, NGC 4450, there it's mentioned. And what you see on the top is, after you've done the dynamical model, of course you have a 3D, so you can view it from any direction. This is from the edge-on view. And you see 3 types of orbits on there, and on the bottom you see the face-on view with the same 3 types of orbits. So why picking these orbits? Because of course there are thousands that you make. And picking these orbits, this has to do with if you look at the orbital structure. And the orbital structure is yes. So the orbital structure, what we don't try to represent that here as function of radius in the galaxy, is here a kind of normalized angular momentum around the short axis, the C-tubes. As Thorsten already said, these are typically the backbone of these galaxies, except if you go to the highest mass. So 0 means Roach-like orbits. So here we pick 1, that's the green one, and you see it goes out of the plane, and it has some kind of random motion. Then you have these nice, very high angular momentum orbits. That's the red one. You see it stays in the plane, and it's more or less rather round, going around. And this particular galaxy also has a lot of counter-rotating orbits, and representing 1 by blue. Okay, so this is what the model gave us. Is this a surprise? No, not at all. Because if you look at the velocity field of this galaxy, you already see that something is happening, because you have here closer to the plane, you have rotation in one direction, and if you go up the plane, rotation in the other direction. These are 2 counter-rotating disks. So this is obvious. But there are many, many galaxies for which counterfeitation happened. This is not obvious from the kinematics. So this method has been developed and applied to early type galaxies. And what we want to do, for example, CLIFA, many spiral galaxies can be extended to spiral galaxies. I'm not going to go in details. People want to know, please come to me or come to lab results here. I'm going to present some preliminary results by posting in our book, Link2. And here's one example. So this is spiral galaxy from CLIFA. The image, here is the data, the feedback, and the dispersion, and here is the fit with the Schwarzschild method, using the R band as the light trace. What you get out of that, of course, is the mass distribution. So as a function of radius, you get the total mass in black, and you can also get the mass in stars. And of course, through subtracting both or modeling in, you also get a handle on the dark matter. So this is robust measurement of, for example, dark matter fraction out to a certain radius. Showing here is also 3.6 micron because we were worried, of course, about dust extinction. So for many of these, we also have near-infrared imaging so that we can check if there's any systematic effects. Okay. What is more exciting is that you also get